the end of last class, this was the version of Bayes' theorem we had sitting in front of us. And I said, I get it, but I use the tree diagram to make the table. And then once I have the contingency table, it's easier to work directly from that than it is to work through the formula. The contingency table doesn't just have to be 2 by 2. We did positive or negative drug test with the chance of using drugs. So does the person use drugs or not? Does the test show positive or negative? So we really had a 2 by 2 table, and allowed me to use this version of Bayes' theorem. But if I have more options, Bayes' theorem still works as long as those options satisfy 2 criteria. They have to be mutually exclusive and collectively exhausting. What the actual does that mean?
Collectively exhausting.
What's collectively exhausting
It
mean?
means that whenever you hit one, it will add up to 100. So you've used every single possibility out there.
So collectively exhausting means I cover all the options. In this version of the formula here, we have B and B prime, B and not B. Those are collectively exhausting. You're either in B or you're not. Mutually exclusive. What does it mean for 2 events to be mutually exclusive?
They don't depend on each other.
That's independent, and unfortunately has nothing to do with exclusiveness. What does it mean to be mutually exclusive? Promise you I've used this term before. You should have it written down somewhere. It went with our Venn diagram pictures.
Like the same 2 things only happen. The same 2 things happen.
So can you see it? Can you describe to me a picture? Because there was a Venn diagram picture that went with this phrase.
The inside of it, right?
The inside of we had the 2 circles.
Yeah.
And then there was something special when we said they were mutually exclusive. Draw in the air funny, I can see you. The or was both of them, right? It could be in one or the other or in both. The and was the piece in the middle. Mutually exclusive meant that there was no middle. The 2 circles had no overlap. They were separate. If you were in one, you couldn't be in the other. There was no mutual that was excluded. So literally the wording itself means that there's no overlap between them. I'm either in B or not B. I can't be in both. That's exclusive. Collectively exhausting means they cover all the options. Mutually exclusive means there's no overlap. So in this version of the formula 15 right here, I only have 2 options. Either the person takes drugs or they don't. Either the test was positive or it was negative. If I have more options, then there is a larger version of Bayes' theorem. And again, this is a formula that you can use, but I'm the kind of guy who want to draw the picture. This, instead of just having B and not B, I have B1, B2, B3, B4, up to Bn. And those are mutually exclusive and collectively exhausting. And in order to reverse my condition, I have to add up all of the bottom ones, not just B and not B. I have to add up the chance of A with B1, the chance of A with B2, with B3, all the way up to Bn. So down here on the bottom, I have that conditional probability set up.
For a question, because I'm doing coding in this, the slash
The pipe.
is in A
Given. Given B. So here it's our version of the pipe is the conditional. That's A given B1, A given B2. There's an example right here. Example 5.8 talks about trauma centers. And if a person goes to one of 3 different trauma centers, what's the chance they file a lawsuit? So all of these are in this same setup, but now instead of having 2 options, I've got 3 going on. So my conditional probability equation gets larger in the bottom. I still think making the tree and then the contingency table is of more use than just the formula. But that formula on page 180 does help us a lot. In general, I think Bayes was actually a very smart guy to be able to say not only does it apply to just 2 options, it applies to more. Larger and more general. Oh, goodness, my handwriting is stinky today. Larger and more general version of Bayes, page 180. All of my probability ideas start with that. Way back when we started this, we said I need to be able to count things. How many ways did what I want happen out of how many times I did the experiment? That was my empirical probability. When I did theoretical probabilities, how many ways can I get the result I want out of how many total ways? So one of the realistic things I can ask is, how do I count really big sets? So when I think about the probability of an event A, that is the number of ways to get A out of the number of ways to get anything, regardless of what I'm counting. So in some cases, it literally does depend on the things we are counting. We talked about picking cards, right? Talked about rolling dice. So let me start with a question I'm pretty sure you answered. How many ways are there to get any result at all if you roll 2 normal dice? How many different things can happen when you roll 2 dice? Because
There's 6 things that can happen on one dice. On the other.
you multiplied. Why am I allowed to do that? That's exactly the correct thing to do. But why multiply? It turns out that this is something called the fundamental counting principle. Or, to steal from a relatively easy, I'm going to call it the multiplication principle. If there are n1 ways to do thing number 1 and n2 ways to do thing 2, then to do both of them, there are n1 times n2 ways. And this idea extends to more. Anybody play Yahtzee? No? There are 5 dice. How many ways? How many possible outcomes are there if I roll 5 dice? A bunch. Grab your calculators. If I roll 5 dice, it's going to be 6 times 6 times 6 times 6 times 6, or 6 to the 5th power, which is big. 7,776. Who owns a car? What's a Pennsylvania license plate look like? What's your license plate? Do you know your own license plate number?
KXN, and I forget the last numbers on there.
How many numbers are there? There are 4 numbers, 3 letters and 4 numbers, and in the middle is the keystone, right? So the Keystone State, yay. How many possible license plates are there in the state of Pennsylvania? I can answer that question because I have to fill in 3 letters and 4 digits. How many choices are there to fill in this letter? How about the second letter? And this third letter? How many choices go here? I use any number you want, right? 0 through 9 for each of these. So in order to figure out how many license plates are possible in the state of Pennsylvania, all I have to do is multiply all of those together. This is a very large number. What do you get? By the way, I can again abbreviate. I can write this as 26 to the 3rd power times 10 to the 4th power. Tony, what you got?
1.75 million, 760,000.
Say that again. I could have sworn you said 1.75. Okay. Thank you. I feel better. By the way, the population for the state of Pennsylvania isn't quite 14 million. We have way more license plates than people. You could staple a license plate to every human being's butt in Pennsylvania, and then you'd still have leftovers. I want you to create a password. Your password must be at least this long. Right? Don't we go through this every couple of months? All right, wait a minute. I'm going to do a short password. Your password needs to be 6 letters. How many possible passwords exist? $15,776. How'd you get that number? But this includes passwords like A, which are kind of dumb, right? But it's a allowable password. If I said you're allowed to use letters that are lowercase or uppercase, what would I change about this?
Double the 0.6.
So it would be 52 to the 6th, which is much, much larger than just doubling this number, right? Because I'm going to double it 6 times. I know passwords here, uppercase and lowercase letters, digits, and symbols. So if I'm allowed to use all of those things, well, I've got 52 with the uppercase and lowercase. I've got another 10 for all the numbers I can use. And then there are a bunch of symbols I'm allowed to use, but a bunch I'm not. Let's call it another dozen symbols. We're looking at what? 76, 78 different characters around? What's 76 to the sixth?
Around 199,699,928,576.
Three more digits longer than this. This is why, by the way, that's only 6 letters, right? Your password to get on the Seton Hill internet needs to be at least 8 characters long and needs to be no more than 16 in most cases. I think they changed that a lot. They might even step that up because now I've got to go through all 178 billion of them to try and break your password by brute force. I'm going to be here for a while. This also does not cull, restrict, or put any other information into the password. You could use A if you really wanted to. You could use 1, 2, 3, 4, 5, 6 if we were allowing numbers. Dumb, but you could. So what if I want to change that? What if I want to put some restrictions in? I'm going to make a change. You're not allowed to repeat things. If I was dealing with my rolling dice, would kind of be difficult, wouldn't it? But let's think about what the other example I used in class. Think about picking cards from a deck, right? I have a deck of cards. I want you to pick 2 of them. You take a card. I don't know what card it is. But if this is a regular deck of cards, can you get that card again? Okay. I've now worked in this idea of not being allowed to repeat myself. Well, if that's the case, then the number of choices I have at each step, I wrote down my number of choices at every step of the way here. My number of choices change. There are 6 of you. If I wanted to line you up against the wall up there, who's going to go first? I've got 6 choices, right? But who's going to go second? I no longer have 6 choices because somebody's already standing. Okay. So we said there were 6 choices here. How many choices here? Because somebody's standing. Keep going. A decreasing count like this is called a factorial. Whatever number you want, positive, whole number, is given the symbol with an exclamation point. That's not n, that's n factorial. And it means you start at n, and then you subtract 1 and multiply, subtract 1 again and multiply, and you keep multiplying all the way down until you hit 1. By the way, that means that this expression right here is 6 factorial, which turns out to be a fairly reasonable number. Factorials get really, really big, really, really quick. Grab your calculator. There is a factorial button on your calculator. At least there should be. You know where it is? If you have a calculator that has any probability or statistics functions on it, you will have a factorial button somewhere. If you've got a graphing calculator, the factorial button is hiding. Hit the math button here. And there's a whole menu with a bunch of stuff. The fourth column heading says PRB for probability. If I go over to that, there's an exclamation point right there. So if I say I want to do 6 factorial, I say 6, math, go to the PRB column and go down to option 4. And there is my calculation for 6 factorial. Here's the problem. If I shuffle a deck of cards, I am taking all 52 cards and putting them in any order. We can think of that as like lining up the cards, right? So I'm lining up the cards by shuffling a deck. How many different ways are there to shuffle a deck? There's that many ways. 52 factorial. I want you to understand, just for a rough idea, 10 to the 67th power. So I got to move that decimal place this way 67 times. In seconds. The universe is only roughly 4 times 10 to the 17th seconds old. If you shuffled a deck of cards every second since the Big Bang, since God said, let there be, and there was, you started shuffling that deck, you wouldn't even be 1/1,000,000th of a percent of the way through. Every time you shuffle a deck of cards, it is most likely you are creating something that no one else in the universe has ever seen. Because there are that many different ways to do it. What's the chance of exactly 2 of you coming up with the same shuffled deck? 1 in that. Not likely to happen. There is one interesting throwaway here. You'll notice that there is not a real good way to figure out what's going on with numbers that are fractions. The idea of a factorial requires n to be a whole number. There are ways to change that. That's well beyond the scope of this course. But there is a number not listed up there that I do want to use. If we think of lining stuff up, I'm going to line up all of my Olympic gold medals. I put them on the table right here in front of you. You see them? How many ways can you arrange all of my Olympic gold medals? The empty way, because I don't have any. That's the only way to do it. So lining up nothing happens one way. 0 factorial is 1. That's a really weird idea. I promise there's a reason for it. I'm not just making this up to make it up. Questions? The whole reason for me introducing factorials is to figure out how to arrange collections, to count them. When I play a game of cards, I don't get all 52 cards. We shuffle and I get some of them, right? So here's a question for you. A standard hand in poker is 5 cards. I'm going to lay out 5 cards on the table. How many ways can I do that? Oh, wait a second. I don't even need a factorial for that. I can think of it just like, here are my 5 cards, damn it. How many choices do I have for this one? And I go down 1 each time, right? And I multiply. Because, Anthony, that's what you told me to do. Now, I look at this and I think of this a little bit different. Instead of thinking of the cards that have been laid down on the table, I also think that I'm holding the deck with the rest of them, right? I laid out all 5 cards, but I still have the rest of them. Do I care about those? Because those are my 5 cards, these aren't. So I could think if I took all of the cards, put them in some order, and then gave you 5 of them and kept the rest. I took all 52 cards and put them in order. I took the remaining cards and put them in order. Because, when I ordered all the cards, I gave you the top 5, 1, 2, 3, 4, 5, in order, and I have the rest of them. These don't count. I need to remove them from this giant gargantuan number that we came up with. Well, if I multiplied to get that number, to take these away, I'm going to divide them out. This is exactly equal to this. If you think about the factorial, that would start at 52, go to 51, go to 50, and keep going until we got to 3 and 2 and 1. The one here on the bottom would start with what number? What's 52 minus 5? It would be 47. And it would go down until we got to the end, right? So what would happen is everything from 47 down on the bottom would cancel with everything from 47 down on the top. What would be left behind would stop at 48. This is an ordered selection. And as an ordered selection, because I laid the cards out in order, we call this a permutation. So this is a way to make an ordered collection. By the way, remember where that factorial button was? Let's go back to where that factorial button was. Math, PRB. Hey, wait a minute, what's above the factorial? There's my permutation symbol. If I type 52 and then I get that symbol and then I type the 5, it'll do this calculation automatically. And that's the same number you get, 311,875,200, is the same number you get if you do 52 times 51 all the way down to 48. I just did it in one fell swoop. So that's how many possible 5-card selections I can make from my deck. There's just one problem. That's not 100% accurate. Because what happens once I give you those 5 cards? I dealt them to you. What do you do with them? Ideally, you pick them up and look at them, I hope. You're going to play the card in the hand of poker blind? You pick up your card and you look at them. Once you pick up your cards, what can you do with them? You can rearrange them, can't you? My ordering doesn't matter anymore. Okay, wait a second. Wait a second. These are ordered collections. If I don't want to care about the order, I have to make this number smaller, because then getting ace followed by king is the same as getting king followed by ace. They're equivalent. I shouldn't count those separately. I should count them once. I have 5 cards. How many ways are there for me to rearrange my cards. I promise it's not a very big number. What do you got, Chris? You're staring at your calculator, just tell me what's on it. Because that would be 5 choices, 5 choices, 5 choices, 5, 5, right? So say that again. Don't do the calculation, just tell me what you just said.
That'd be 5.
Which is our factorial, isn't it? 5 times 4 times 3 times 2 times 1. Now, give me that number. $120. So really, I want to take this number that we got and divide it by 120 because each of those 120 different orderings would be counted once instead of counting them all 120 different times, right? Unordered selections would be NPR divided by R factorial. So because I got 5 cards, I divided by 5 factorial. So if I take this number and I divide it by 120, because that's what you came up with, I get 2,598,960. 2.6 million. Anybody who plays poker has that number somewhere in their head. It's printed in the information card in every poker deck. If you buy a pack of cards that says poker on the outside, it'll have a card with this information in it. That number will be there. Oops. That number. Oop. That number. Now that you can read it and it's not glared off the screen. But what that means is that I do this formula. Well, let's go back and look at this. This NPR thing is n factorial over n minus r factorial. That's how we got this number right here. If I add this extra one on the bottom, I'm going to get n factorial over n minus r factorial, and there'll be another r factorial on the bottom. This is now an unordered selection. We call this a combination. And we write NCR. C for combination, P for permutation. I like to think of this like lottery tickets. You go in and you're going to buy a lottery ticket. You got to fill out your little slip, right? If the order mattered, you would have to pick each number in order. You have to pick them one at a time. That's like laying down our cards one at a time. Here is your first card, here is your second card, here is your third card, and so on, right? That pick one at a time is the P for permutation. But if I just get a bunch of cards, I reach in with my hand and scoop them up. There's the C for combination. To me, this is kinesthetic. This is body, this is movement. I pick them one at a time, that's permutation, that's ordered. I grab the whole thing, that's unordered. That's combination. A lottery is almost always an unordered selection. Combination numbers are smaller than permutation numbers because we had to divide by something extra. Somebody go to the lottery website, PA Lottery, whatever it is, palottery.com. How big is the Mega Millions lottery this week? Yeah. $520 million. Okay, how do I play the game? I have to go in and fill out a card, right? When I go to fill out the card, I have to pick 5 numbers from 1 to 70, and those are usually white numbers. And then I have to pick 1 from 1 to, I think it's 25. and that's the red number. Like with the Powerball, your numbers go from 1 to whatever, and then the other number, so there are two different kinds of numbers. Mega Millions does the same thing. So here's my question. How, 1 to 24? Thank you. Great. So here's my question. How many ways can you fill out a Mega Millions ticket? How many different possible tickets are there? Well, out of these 70 numbers, you're going to choose 5 of them. Does the order in which you select them matter? So that would be 70, choose 5. A combination. And in the red numbers, I only have to choose one of them, right? So it's going to be C1 out of the 24. I have to do both these things. I don't know what these numbers are yet. But since I have to do both of these things, what do I do with these numbers? I multiply them together. So now I can actually work out what these numbers are. I know before I do any math, if you have 24 things and you only have to choose one of them, how many ways can you do it? Oh, that's nice and easy. So it's going to be big ugly number times 24. I just need to work out this big ugly number first. So out comes my calculator again. And I go 70, math. I go back to the PRB section, and there's, lo and behold, is my combination option. Option 3. And I tell it to choose 5. Take this number, multiply by 24. Oh, you said $525 million? And tickets are $2 a pop, right? Multiply this number by 2. If I wanted to buy every possible ticket, it would cost me $580 million. I'd only be making 520. I'm losing money here. It's a bad idea. By the way, it turns out, according to the National Weather Service, the chance of being struck by lightning is 1 out of 15,300. At some point in your life, the chance you will get struck by lightning is 1 out of 15,300. What's the chance I get struck by lightning twice? Those are independent events, right? So we multiply this by itself. 15,300 times 15,300. It would be 1 over this number, right? Please notice this number is smaller than this one. You stand a better chance of being struck by lightning twice than you do of hitting the Mega Millions. And this is why lottery is a tax on people who are bad at math. I love the idea, but it's more likely for me to get hit by lightning twice. Most of the time, when I'm working in a probability, I don't actually need to write out the sample set to count it. I didn't write out all the possible hands in a poker game to figure out that there are 2,598,900 of them. I just counted how many ways it could happen. And then I can say, all right, we're going to play a hand of poker. Anybody play poker? What's the best possible hand you can get in a game of poker? Royal flush. And a royal flush is?
Yeah.
You're missing one. Same suit.
Yeah.
Okay. But I need a 10 in there too, right? 5 cards in a row. That's a straight. The royal, because all of the face cards are in there. Highest straight you can get. Them all being the same is what makes it a flush. Which means there are only 4 ways to do this. You could do it with them all being hearts, diamonds, clubs, or spades. That's it. So the chance of getting a royal flush is 4 out of 2, 5, 9, 8, 9, 6, 0. How many ways can what I want to happen happen? Out of how many ways something can happen? If I can count the number of ways my event can occur, I can figure out its probability without listing the sample space, without going through all of the ginormous decision tree or listing. I can still come up with a number. By the way, this is really, really rare. I am 56 years old. I've gotten 1 in my entire life. I have not been playing poker for decades, but still. Questions? Student IDs, barcodes, final exams, arranging books on a shelf. Look, there's a lottery right here. All I need to do is count the number of ways I can get what I want versus the number of ways things can happen. Most of the time, that is sufficient. But then I have to use my and, my or, my not ideas. If I need conditionals, I've got to work them in as well. So having the ability to count large sets then allows me to find all the probabilities I want to work with. Whew. All right. I have enough time. I'm going to start the next chapter. Today is listed as both. We have finished chapter 5, which means the homework is due 2 class periods from now. Normally I would say, hey, it's Wednesday. That means it's Monday. But what's Monday? Fall break. So it's due Wednesday when we get back. But let me give you the beginning, chapter 6. We talked about gathering information and doing descriptive statistics, right? Mean, median, mode, standard deviation, quartiles, interquartile range, outliers, unusuals. We did all of that idea. Chebyshev's theorem, all of that. And I said, this describes the information we have. But when we're talking about gathering that information, we talked about bias, samples, and the way in which we did samples. And then I said, does the information I have accurately reflect the larger population? Because if I take a sample, I've only got some information, I'm trying to make predictions about the larger. That means I need to make some assumptions about the way the larger group behaves. Those assumptions are called distributions. A probability distribution represents the result of doing an experiment multiple times. We're going to call that a random variable. You'll often hear this experiment referred to as a stochastic process. Stochastic is a fancy word meaning it happens a finite way, a finite time. It's just bonk, bonk, bonk. We do it over and over. I am phrasing this in a slightly different form from the textbook. The textbook talks about this as a mathematical rule. I know that's technically a right definition, but it's a pain in the ass to understand. So we'll get there. A random variable means we did something, here's the result. Discrete. Where did I hear that phrase before? In this course. My data types. And discrete meant
Yeah.
a whole number. So like 1, 2, 3, we're talking about distinct categories. Even our qualitative data was distinct, but when we did quantitative data, we talked about it being not continuous, but chunked, discrete behavior. I can talk about countable number of absences or number of times the coin came up heads. All of these options, how many phone calls were made to the office of the registrar today? If I think about how many times has someone been absent from class? When the semester ends, there's an upper limit to that. This class meets 3 times a week for 15 weeks. There are 45 class days. I can say out of 45, this is how many somebody missed. If I talk about the number of phone calls that came into the registrar's office today, the answer could be in the hundreds. It could be 3, but it could be 300, right? I don't know how busy the phone is over there. But if I say the number of phone calls is between 0 and 300 on any given day, then I can look at the numbers from 0 to 300 as my outcomes. A probability distribution assigns a probability to each of those outcomes. And that's what they mean by a probability being a rule. Here's an outcome. Tell me what the chance of it happening is. What is the chance that a student missed exactly 6 days this semester? What is the chance a student misses 12 days this semester? What's the chance the registrar got 13 phone calls today? What's the chance it got 100 phone calls today? Each of those will have a probability assigned to it. There are two rules that I'm going to still deal with for my probabilities. Each probability has to be a number between 0 and 1. And the sum of all the probabilities is 100%. These outcomes are mutually exclusive and collectively exhausting. I hit the clock. We'll pick up more on Friday. I will see you all then. Have a wonderful rest of your day.